Okay, I'm going to do a quick video here that's going to describe together problems 53 and 55 for chapter 12. Now, before I get to the actual problems themselves, I want to direct you to a slide that is in the 12.7 and 12.8 PowerPoint. It talks about the collision model and how chemicals have to collide the right way in order for a reaction to occur. Now, what I'm doing is jumping down here to the slide that has all this math on it. And the take-home message is this what's called the Arrhenius equation. Okay, now the collision frequency is just a method of actually quantifying the collision. You don't have to necessarily know that, but you have to know the end result of the Arrhenius equation. Now, first of all, I want to kind of explain that this one right here is for one set of conditions, and this one over here is for two sets of conditions. Now, the other thing that you'll notice about this equation right here is that you have y equals mx plus b. So we can use that to graph. So both 53 and 55 are going to deal with the Arrhenius equation. And that's when, and the big thing with the Arrhenius equation that you'll notice is all of a sudden now we're dealing with temperature dependence. We've talked about the fact that they were temperature dependent, but we hadn't done anything with temperature. So how you recognize to use these equations is when you're talking about temperature dependence. The other thing you'll notice is we've got the ideal gas constant, but remember it's going to be the 8-point version that has joules in it, and I always remember energy is joules, so that's how I know which one to use. Okay, now let me go ahead and show you, it does this every time. Okay, let me go ahead and show you the answers that are worked out, and then we can kind of talk about that stuff. Alright, now first of all, let me bring this down. Okay, so for 49, here you have just the generic form of the graph. Your reactants, your products, delta E for energy. And the only thing that I wanted to point out is this red line right here shows a catalyst. A catalyst lowers the activation energy. Alright, now let's jump to 53 and 55. Now if you look at 53, if you don't have your textbook out, go ahead and pause it, take your textbook out and read 53. But 53 gives us the rate, it says the rate constant for gas phase decomposition is the following, and it says has the following temperature dependence. So again, there's your cue that we're dealing with the Arrhenius equation. You've got temperature values and you've got lowercase k values. It says make the appropriate graph using these data and determine the activation energy of this for this reaction. So as a reminder, I've just redone the y equals mx plus b. What we're looking for is the natural log of k versus 1 over t. Will help, a slope is going to be the activation energy over r. So we can use the graph to help us figure it out. Again, there we go. So on this one, you've got temperature. We got to do 1 over t because that's what we have to graph. We've got k, and we've got to do the ln of k because that's what we've got to graph. So whether you do this on a graphing calculator or you sketch it, again, you get a really rough sketch. We get the straight line with a negative slope, so we can find it. So our slope is going to be negative EA over r. So we find our slope using same thing like we've done, delta y over delta x. Okay, we solve for our slope. You want to make sure to keep in mind the units on these things. We find our slope. It's going to be negative 12,500. We set that equal to the negative activation energy over r. So we can solve for an activation energy of 104,000 joules per mole. If you see this in kilojoules per mole and it's not specific, totally acceptable. At this point, we know how to go between joules and kilojoules. So again, it's just using y equals mx plus b to get the right version of the graph. Okay, now for 55, if you look at 55, it says at 25 degrees Celsius, the first order rate constant for a reaction is 2.0 times 10 to the third 1 over seconds. Again, first order, just as a reminder, pointing out that unit here is 1 over what your time value is. It gives us the activation energy. Okay, it's got 15.0 kilojoules per mole. You also, if you want to go to joules, I really don't want to, don't show me this message. There we go. Okay, put the little times 10 to the third up there if we want to go right to joules on this. We want to know what is the value of the rate constant at 75 degrees Celsius. Okay, now, first of all, again, we have two separate sets of conditions here. So what we're looking at is we have a first temperature and we have a second temperature. And so that's why on this one we need to use the Arrhenius for two conditions. As a reminder, Arrhenius for one condition, you've got the ln of k, activation energy. This is what we just did, y equals ms plus b. Well, here we have k1, We want to know K2 at 75 degrees Celsius. They gave us the activation energy, so although the math is a little bit ugly, it's just a matter of plug and chugging. Okay, we've got the K, and this is one thing that you need to keep straight. You know, the K2 is over the K1. This is just really common mistakes I see people making these. This is a minus sign right here. Okay, so again, it's set up, and then it's just a matter of plugging and chugging. Why did this have to be in joules, the activation energy? Because my R value has joules in the unit. So that's why when you plug it in, it has to be in joules. All right, now when you go ahead and plug and chug for these, there's a couple different ways to do this. When you get down to 0.87, I think one of the easiest ways is to do the e to the x on the other side in order to reduce it down, but you should get 4.8 times 10 to the third, again 1 over s, because it's a first order reaction. Okay, it's some different things. Remember, the key to remembering to use Arrhenius is that you've got the temperature values out there.